Okay. If you remember, on Tuesday we talked about cache memory and different mapping methods. We just covered direct mapping on Tuesday, and today we will continue on other mapping methods and do some examples on each mapping method. Okay, so let me see if my I don't know why my screen doesn't get updated fast. So anyway, I write something, it takes like few minutes to be shown on your screen. So I need to figure it out to see what's wrong. Let me just reconnect to the, let me, no, it's not a cable problem. When I connect my tablet to the internet and start Zoom, I get some DLL errors. I think I need to reinstall my Windows. I get some DLL and some files errors. And as soon as I get those errors, I see that the screen gets disconnected. So I believe that I need to reinstall the Zoom or like the Windows. But by the way, of course, you cannot do that now. So let me just disconnect my tablet from here and reconnect it again to see. Hopefully it works. Okay, now it's working. I hope that it works. Okay, so in direct mapping, I said that we consider three different fields: tag, block, and offset. Okay, one thing that is important to know, let's assume we have CPU here, we have cache memory here, and we have main memory here. Okay, so we have three different memories and still the same problem. Oh, okay, it's coming. So I need to move slowly because uh, let me do something else. Let me go ahead and I know what to do. Just give me a minute. Okay. Okay, and now let's see if again it's still it's lag. I will work with my OneNote instead of PowerPoint. So I said assume we have the CPU, we have cache memory, and we have main memory. What is important here that the CPU doesn't care about the cache memory. The CPU execute the program in a way that it assumes all the program is in the main memory. But every time when it wants to fetch the instruction, first check the cache memory. If the data is in the cache memory, fetches the data from cache memory. And if the data is not in the cache memory, fetches the data from the main memory. So the address bus, the address of the instruction or the data that the CPU works with, that is like the address of the main memory, not the address of cache memory. So any address location of the memory has a specific address. The CPU considers that address to access the data from the main memory. But before getting to check the main memory, it first checks the cache. If the information is in the cache, grabs the data from cache. Otherwise, goes to the main memory and like check the main memory and gets the data from the main memory. So it's the reason that why even when we like work with the cache memory, the address field is the same as the address field of the main memory, because as I said, the processor assumes that like there is no cache and directly working with the addresses that are related to the main memory. And we have a tag, we have a block, and we have offset. And if you remember, I said that each cache or main memory is divided to different blocks. Any block is several bytes. The block can be 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes. So any number of bytes which are grouped together are considered as one block. Okay. So the block, by the way, cannot be like 5 bytes. The blocks are 1 byte, 2 byte, 4 byte, 8 byte, 16 byte, 32 bytes in the like power of 2. Okay, so one block cannot have like 61, not 61, 9 bytes. It has to be like in the form of power of 2. Okay, and now that we know each block in the cache can be mapped by several blocks on the main memory, how we can know which block of the main memory is copied or it is existed in the cache memory. And I said that we use the tag field to determine if the data in a specific block of the cache is from a specific address of the main memory. And so here is uh, those three fields. Okay, let's go ahead and see what we have here. We have an example. Here we have an example, and we want to learn how to solve the problems related to cache memory. The example 161 says that consider a byte addressable main memory consisting of 4 blocks. So number of blocks are 4. And the cache with 2 blocks. So the cache memory has 2 blocks. Well, each block is 4 bytes. Each block is 4 bytes. Each block is 4 bytes. Okay, now we want to like see how to map the main memory address to the cache memory. Okay, when we say we have 2 blocks in the cache, means block 0 and block 1. So it means that block 0 and 2 of the main memory are mapped to block 0 of the cache, okay, and block 1 and 3 of the main memory are mapped to block 1 of the cache. Okay, so if we have 4 blocks in the main memory, B1, B2, not B1, let's start from B0. B0, B1, B2, B3, this one is main memory, and here we have the cache, which only has B0 and B1. So we know that B0 of the main memory will be mapped to B0 of the cache, B2 of the main memory will be mapped to the B0 of the main cache memory, B1 of the main memory will be mapped to B1 of the cache, and B3 of the main memory will be mapped to the B1 of the cache. Okay, and the same like rules, if you remember, I said that Y is X module number of blocks. So we should calculate X modulate of 2. So 0 modulate of 2 is 0, 1 modulate of 2 is 1, 2 modulate of 2 is 0, and 3 modulate of 2 is 1. Okay, so let's go ahead and see what we can do. The first thing we should consider in this example, we need to form our address field. The address field consists of tag, block, and offset. Okay. How many blocks the cache has? 2 blocks. Because cache has 2 blocks, for addressing 2 blocks, we need 1 bit. So the block field of the address is 1 bit. What is the size of each block? The size of each block is 4. How many bits do we need to address or select 4 bytes? We need 2. Okay, so we need 2 bits to 2 bits to select one of the main memories. And finally, we know that the main memory, the problem says that the main memory is, let me find it up. Oh, okay. So how many bits, how many bytes is the main memory? The main memory consists of 4 blocks times each block has 4 bytes. So main memory has 16 bytes. For 16 bytes, we need 4 bits to address 16 bytes. So the entire length of the address field should be 4. So 2 of them are for the offset, 1 of them is for the block, and one bit will be left that we use for the tag. Okay, so it's the way we determine the number of bits for each field in a cache memory addressing. Let's see one example here. It says that suppose we need to access the main memory address 3. Main memory address 3. If we write the theory in the binary form, the binary form of theory will be 0011. Okay, so based on what we saw, two of them is for the offset. So 1 is for the offset. One of them is for the block, and one of them is for the tag. So in each block, in which offset of the block the information will be stored in in the byte number 3, because 1 is 3. In which block the information will be stored? Block number 0. So we go to block number 0, byte number 3, and here is the mapping address of the main memory. Okay, and by the way, what is the tag? The tag is 0. Let me show you one more example to make sure that you all understand this. I have a question. Tag 1, the 16 stands for the bits. Which 16? I get a question that says tag 1, the 16 stands for the bit. Which 16? How do we determine how many numbers go in the offset section? Like the offset section, like this field is the offset section. So this field is offset section. So now how many numbers go in offset section? Here is 1 1. 1 1 is like we need to go to the fourth location of the offset, because like the offset field is 3. And the other question, no, tag 1 was the answer to earlier. The 16 is the base of 3. Oh, I got it. Okay, so let's go ahead and see like this example in another way. So here we have two addresses from the main memory. One address is 0011. The other address is 1011. If we put these addresses in the fields, we see that both of them are mapped to the same block. Both of them are mapped to the same block, and both of them are mapped to this to different offsets. So the one of them will be mapped to offset 1 1. The other one will be mapped to offset 1 0. Let's show it in the memory. In the memory, 0011 is this memory location. This memory location. This memory location will be stored in block 0, which is here, block 0. Which offset of the block 0? Offset 3. Offset 3 is in fact the last location. And the tag will be, the tag will be 0. Okay, so the tag will be 0, and the information is. And by the way, I think something is wrong in this slide, because each no, that's correct, because we move the data in a block, not just a single byte. Okay, that's fine. So the map is the tag is 0, and we put the tag 0 here. Let's look to this other example. Let's look to the other example. The address 1010 in the main memory is here. Okay. And which block this address will be mapped? Block 0. Okay. Which offset? Offset 2, which is here, because the first offset is 0 0, second offset is 0 1, the third offset is 1 0, and the last offset is 1 1. So because the offset is 1 0, it will be mapped in this location, and the tag will be 1. Okay. And by the way, one thing that I should mention that I forgot to mention a few minutes ago, whenever we want to move, why my eraser is not working? Let me just eraser is not working. Whenever we want to access to a memory of the main memory, we transfer the entire block from the main memory to the cache. It's very important. Okay, so in the on the left, when we want to access the last byte of the block 0, we transfer the entire block to the main memory. And so it's the reason that why we just use one tag for each block, because all the bytes in the block, they have the same tag. Any question? Let me go ahead, and I hope that my pen is working. Okay, so the next example. So this one will be easier, because we already learned how to map the main memory on cache. So this one is easier. So assume a byte addressable memory consists of 2 to 14 bytes. 2 to 14 bytes. So it says that the entire address field should be 14 bit. 14 bits, because Memory consists of 2 to the power of 14 bytes. Okay. The next part, cache has 16 block. Cache has 16 block. Okay. And each block has 8 bytes. Okay. Each block has 8 bytes. The first thing, cache has 16 blocks. How many bits we need to address one of these 16 blocks? Of course, we need 4 bits. So 4 bit, we need to address one of these blocks. Each block has 8 bytes. So how many bits do we need to address one of these 8 bytes? 2 to the power of 3 is 8. So we need 3 bits to address the offset, and the remaining for the tag is 14 minus 4 minus 3 is 7. And 7 bit will be for the 7 bit will be for the tag. So by the way, the problem doesn't mention that how many blocks are in the main memory. How we can know how many blocks are in the main memory? We know that there are 2 to the power of 14 bytes in the main memory, and each block is 2 to the power of 3 bytes. So if we divide those two numbers, it's remaining like the result is 2 to the power of 11. So 2 to the power of 11 tells that we have 11, 2 to 11 blocks in the main memory. Okay, 2 to 11 blocks in the main memory. Okay, so now that we have each field size, let's move to the next part of the problem. Next of the problem, it's next example, in fact. Next example, again, it's like another example. It says that we have a memory consists of 16 bytes. Because memory consists of 16 bytes, it means that the entire memory address field should be 4 bits, because 4 bits, 2 to the power of 4 is 60. Divided in 8 blocks. So when it's divided to 8 blocks, what is the size of each block? 16 byte divided by 8 blocks. So each block has 2 bytes. So because each block has 2 bytes, we need only 1 bit to address one of these bytes in the block, and the remaining for the tag will be equal to 1. So it's the way we fill these address fields. Okay, let me just repeat it one more time. This example. Let's assume this it's the question given in the test, and I want you to fill out this address field. So you would say this here is offset. Here we have block, and here we have tag. Okay, now in the next step, let's read the problem from the beginning. Assume a byte addressable memory consists of 16 bytes. When it says 16 bytes, it means that the entire address is 4 bits. Why 4 bits? Because 2 to the power of 4 is 16. From these 4 bits, let's move on and see. It says the main memory divided into 8 blocks. When the main memory is divided to 8 blocks and it's 16 bytes, so let's see how many bytes are in each block. So we say 16 bytes are divided in 8 blocks. So each block has 2 bytes. Because each block has 2 bytes, in order to select one of these 2 bytes, we need 1 bit. So offset will be 1. Okay. And the next thing, it says that the cache contains 4 blocks. Cache contains 4 blocks. In order to select one of these 4 blocks, we need 2 bits, because 2 to power of 2 is 4. So 2 bits for block, 1 bit for offset, and the remaining bits are 1. 4 minus 2 minus 1 is 1. So 1 bit for the tag. Okay, so it's the way we like determine the size of each field in a direct mapping. Any question? Go ahead. I see that one of you have a question. Go ahead. If there are 4 blocks, okay. If there are 4 blocks, well, in the main memory, you mean? No, my question, like Kevin asked a question, he says, I have a question. If there are 4 blocks, 4 blocks where? In the main memory or in the cache? Oh, you saying that it says the problem says that the cache has 4 blocks. Okay, if there are 4 blocks, how would you assign it to the 4th cache? It says cache for block 0, block 1, block 2, and block 3. I don't get the question. How would you assign it to the 4th cache? 4th cache, what does 4th cache means? Can you just unmute your microphone and ask your question?
Yes. If you
No, I can hear you. Just
can you hear me?
let me just increase the volume.
Hold on. Can you hear me now?
Okay, yeah, go ahead.
Okay, so it says you have 4 blocks, right?
In the cache.
Yes, in the cache, because that's what it says. Cache contains 4 blocks.
Yes.
But here we say we have only 2 blocks, 2 bits blocks.
No.
Oh, it's 2 bits for the added. Oh, never mind.
2 bits for selecting a block.
Yeah,
With
gotcha.
2 bits, we can select one of those 4 blocks.
Yeah.
Yeah.
Never mind. Completely. Yeah, I
Okay.
caught myself. I
Okay, that's fine. Okay, that's okay. Okay, so if any other of you have any question, you can just unmute your microphone and ask a question. I have one other question. I would think black would have a 1 1 to assign to cache 4, which is yeah, it's the answer to the question that Kevin asked. Okay, very good, very good. Okay, so let's continue. Very good. Now let's move to the next example. So now I'm sure that all of you know how to find out the number of bits for each for each field. Okay, so here it's example. It's the same example or a different example? 6-3. This one is also the same example. The continue of the same example. It says the mapping for the memory reference is shown below. Okay, so here is what we found, and it says that the block 0, 0, the block 0 will be mapped to block 0 of the cache. Block 4 will be mapped to block 0 of the cache. Okay, block 1 will be mapped to block 1 of the cache, and so on. Okay, so it just shows how do they map the blocks. And the address, of course, the address of each block has been written here, and for the cache is being written here. Okay, so it just shows how we can map each block in the cache. Example 6-4. This one, I like this example. So let's learn it together and see how we can solve it. Consider a 16-bit memory address. When it says 16-bit memory addresses, it means that the entire address field is 16. 16. And it has 64 and 64 blocks of the cache. 64 blocks of the cache. By the way, when we have 64 blocks of the cache, it means that we need 6 bits to address these 64 blocks. So in the block, we need 6 bits. Each block contains 8 bytes. Because each block contains 8 bytes, we need 3 bits for offset. And the remaining, of course, is 6 plus 3 is 9. 9 minus 16 is 7. So 7 for the tag. So this one is done. Now it says that the memory reference, like the address that processor wants to access to that address. The memory with address of 0404. Okay, we want to see in which cache memory this address will be mapped to. Okay, so let's just this number is in hexadecimal because it has 0x at the beginning of it. So let's write it in the binary form. If we write in the binary form, is 4 zeros. Number 4 is 0, 1, 0. 4 other zeros, and number 4 again is 0, 1, 0, 0. And if we separate them like in the group of 3, 6, and 7, we will have these numbers. So this address 0404 will be mapped in block 0, in the block 0, and byte number 4. So offset will be 4. Okay, and the tag, of course, is this number. Okay, the tag is this number. So it's the way we find which block and which offset the memory will be mapped. Okay, and by the way, when I want to access to this memory, to this address 0404, and I know that the address is in block 0. When we access to main memory, we transfer entire blocks from the main memory to block 0. So address the offset 000, 001, 010, 011, 100, 101, 110, 111. So these are 8 offsets, and the block and tag feel the same. So entire these 8 bytes, which is one block, will be moved to the cache memory. Okay, so when we transfer the data from main memory to cache memory, we like transfer entire block, not just one byte. Any question? Okay, now let's it's like summary, and okay, that's it. So so it's like a summary of the direct map. So we already discussed everything about the direct map, and we done with direct mapping. Okay, so if I give you some information like like this, if I give you the memory size, the number of blocks, and the like its size of block, and ask you, okay, let me know this address 1A2F will be mapped in which block of the cache. This address is from main memory. If I ask you, tell me this address from the main memory will be mapped uh, to which block of the cache, you should just repeat the same thing we did together. You need to just find out the fields, find the size of the fields, and write this hexadecimal number in the form of binary, and see that which block and which offset and which tags are generated. Okay, questions? Okay. And I recommend you to like review your textbook as well, because in your textbook you also can find lots of so many examples, and it's good to do a practice with on the textbook. Okay, if you don't have any questions, I'm going to move to the next type of cache memory mapping. So far what we learned is direct map, but we want to move to the other type of map. But before that, I want to show you something. Let me just exit from. Let me exit from my PowerPoint and open my OneNote. Okay, let me share my OneNote with you. Share OneNote. Okay. Okay. So we have a cache with 4 blocks. Block 0, block 1, block 2, and block 3. And here we have the main memory. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, that's enough. So it's block 0, block 1, block 2, block 3, block 4, block 5, block 6, block 7, block 8, block 9, block 10, block 11, and block 12 for example. So of course that we know that the number of blocks will be continue until block 15 because they always have to inform of 2 to the power of n. So block 0 will be mapped to block 0. Block 4 will be mapped to block 0. Block 8 will be mapped to block 0. And block 12 will be mapped to block 0. All these blocks will be mapped in block 0 and they cannot like map in any other blocks. So a problem. What's the problem here? Let's say our program wants to access to block 0 of the main memory. Okay, because the data is not in the main memory, it grabs the entire B0 and move it to like to the cache. So let me just, I'm writing the block number of main memory in here. So block 0 of the main memory will be moved here. Next, let's say the program wants to access to block number 3, block number 3. Gets block number 3 and map it to this block. Any question? Is it clear? Okay, of course it's clear at this moment. So we see that 2 blocks of the cache as like is are occupied and 2 of them is still empty. Now let's say that the next line of the program, the main memory wants to access to block 8 of the main memory. It goes to block 8 of the main memory and transfer block 8 of the main memory to block 0. So block 0, this information should be erased and block 8 will be written here. Now there is a problem. You see, we still have 2 empty blocks, but we are not using those blocks because block 8 is exactly mapped at the same location as block 0. So it's problematic because some of the blocks can be like needed 100 times and some of the other blocks might be like needed like 1 time or 2 times. So this one is like a problem or not problem. This one is the disadvantage of cache memory direct mapping because each block of the main memory can be mapped to a specific block of the cache. So we need to erase like the information and write the new information in the like in a single block while we have other blocks available. Okay, how we can just solve this problem? We want to be able to write in the cache memory as long as we have empty blocks. Why should we like keep two blocks empty and just try to replace the blocks in the like other existing values? Okay, so we need to find another mapping method that can solve this problem. Let me explain it one more time. It might be not uh, clear, so let me just again explain it one more time. Okay, so here is block 0 of the map, cache, block 1 of the cache, block 2 of the cache, block 3 of the cache. So the main memory wants to access block 0 of the main, the processor wants to access the block 0 of the main memory. So block 0 of the main memory will be copied in block 0 of the cache. Then we go to block 3 of the main memory. Block 3 of the main memory will be mapped to block 3 of the cache. Then we want to access block 8 of the main memory. So block 8 of the main memory sees that the cache, the block 8 of the main memory should be mapped in block 0. But the block 0 has some information. So those data should be erased and the new block should be overwritten on block 0. And now in the next step, let's say we want to access to block 12. The block 12, not block 12, sorry. The next step, we want to access again to block 0. When we want to access to block 0, we go to block 0. The block 0 it can be mapped in like block 0 of the cache. It was there. It was there. Block 0 was there. But we erased that. Why we erased that? Because it was needed by block 8. And now again, we have to erase block 8 and again overwrite with block 0. So you see that we erasing and overwriting data in block 0 while we have some empty blocks. So it's not good. We like wasting the resources. Some of the blocks are not being used and some of them using like frequently. So how we can just fix this problem? How we can make sure that none of this information in the cache will be rewritten as long as there is an empty block in the cache. So how we can make sure that no data in the cache will be erased as long as there is like empty space in the cache. So here is the answer that we need to go with another mapping system which called associative mapping. Okay, let's see what is associative mapping. Let me share my screen. Okay, so if I the screen and go to the next slide. Okay, so here we want to introduce a new cache mapping called fully associative mapping. Fully associative mapping. Okay, and as you say in this line, it says that in this way, cache would have to fill up before any block are evicted. So before like we rewrite any data on the block, the cache would have to fill up. Okay, and it's good. It has advantages, disadvantages. We cannot say that it's always the best idea. It has advantages, disadvantages. So in fully associative method, we have only two fields, okay? Two fields. One field is called tag, and the other field is called offset. We don't have any like block in the full associative mapping. So here it's an example. It says that we have a 14-bit memory. Because when we have 14-bit memory, the entire address field is 14-bit, and cache has 16 blocks. Because cache has 16 blocks, that's okay. We don't care about number of blocks because we are not going to pick any of those blocks. Okay, we are not going to select any of those blocks because it's not direct mapping. One thing which matters is size of blocks. This one matters, not the like number of blocks in the cache. Each block has a size of 8. Because each block has a size of 8, the offset field has to be 3 bits. And we know that the entire address field is 14-bit, and the remaining for the cache will be 11 bits. Okay, so how does it work? Before I move to the next slide, I would say every time we store, if you remember in direct mapping, we had like data, and we had tag. Okay, we had data and we had tag. And we had different blocks. But here fully associative, we have our cache memory. The cache memory consists of n blocks and divided to two parts. One part is data, the other part is tag, the other part is tag. Whenever we want to transfer data to the data to the cache, we write the data in the first available block, So we don't like to modulate, so we don't like to do a module. So like the address module, the block numbers. No, just we look for the first available block in the cache. We copy the data in the first available block, and also we copy the tag in the same location. Then for the next memory, we move to the next block. Okay, so we continue until the cache is filled up. Okay, and every time we want to access to the data in the cache memory, we need to compare all these tags, to see which one of those is the same as the tag we're looking for. So here is a disadvantage. What's the disadvantage? We have to have a very complicated hardware circuit to compare all tags at the same time to see which of these tags is identical with the tag of our address. But if you remember in the direct mapping, we didn't have to do that. In the direct mapping, based on the block field, we select the right block, the correct block, and we only check the tag of that specific block, because we knew that the address we're looking for is mapped in which block. But here, because the data can be mapped to any of those blocks in the cache memory, we have to compare all the tags together and see if any matching is happen. So it's like a bottleneck of fully associative mapping, it like needs like very expensive hardware to compare those tags together. Any question? Okay, let's you will recall that direct map cache evicts a block whenever another memory reference needs that block. Okay, that's the thing that we already discussed. The second sentence says that with fully associative cache, we have no such mapping. Thus, we must devise an algorithm to determine which block to evict from the cache. Okay, I will talk about like evicting algorithm later, so not now. So let's keep this slide for later. And the last type of cache memory is set associative, which is a combination of uh, direct mapping and indirect mapping. Okay, so let me move forward before I talk about. I want to show you something. Okay, so I want before talking about direct mapping, I want to show you one example, and we can discuss it in for direct mapping. The example 6.7 says that a byte addressable computer for 8 block cache of 4 bytes each. Trace memory addresses 01, 04, 09, 05, 1421 for each mapping approaches. Okay, mapping approaches means like direct mapping, fully associative, and set associative. The address format for the direct map cache is as follow. Let's see how we can how did we find it. So here is like the memory. The memory is like 8 bits, 8 bits. Okay. uh Cache, uh 8 bits, and let me see, for 8 block cache of 4 byte each. So 8 block of cache means that cache has 8 blocks. So the block size like it should be 2 to the power of 3, which is 8. So block field of the map will be 3 because it's 8 blocks cache. Each cache has 4 bytes. So in order to select 4 bytes for the offset, we need 2 bytes, and the remaining the tag will be 3 bytes. Okay, now that we have this mapping, we want to see in which block each data will be mapped. Let's start from address 01. First 01. 01 is 0000001. Okay, so this one is a 01. So 01 will be mapped in block 0, offset like 01. If you remember, I said that the entire addresses of entire bytes of one block will be moved to the cache memory. So the address 00010203. All of these 4 addresses have the same tag and block field, and the only difference is offset. So addresses 0010203 will be moved to the cache. So let's see in this table. It's easier if we look in this table. The same thing that I did in this table. It's explained. It says that address 01 is can be written in this form, and because at the beginning there is like the cache memory is empty, definitely we will have a miss Okay, we will have a miss. You remember what is miss? Miss is like if the processor checks the cache and see the cache is empty. Okay, and let's see the comments. The comment says that if we check cache block 00 for the tag 000, we find that it's not there. Of course, it's not there. And so we copy the data from address 00010203 into the cache block 0. Why all of them? Because address 00, address 01, address 02, address 03, they are in the same block. So address 00010203 will be copied to block 0, and the tag is 0. Okay, so far let me just have our cache memory. The cache memory, how many blocks has cache? 8 blocks. Cache has 8 blocks. So here is 8 blocks. Okay, block 1, block 0, block 1, block 2, block 3, block 4, block 5, block 6, block 7, and the addresses 00, 01, 02, and 03 are copied in a block 0. Now let's move to the next line. The next access is address 04. Address 04 is address 04 is 00001, sorry, 0000101. So which block? The block number 001, and which addresses? Okay, which addresses? So the addresses, we should just consider this offset and put it 0, 1, 2, 3, 0, 1, 2, 3, and we find the addresses. So address 4, address 5, address 6, and address 7. These addresses will be copied to the cache with the tag 0. In which block of the cache? Of course, block 1 of the cache. Okay, so address 4, address 5, address 6, and address 7 will be copied in like in the block 1 of the cache memory. Next, let's continue. We want to access to address 09. I want to make sure that you hear me. Just say something.
Yeah, I hear you.
Oh, okay, good. So the next
Yes.
address, good, thank you. The next address is 09. 09, if we write 09 in the binary form, is here. This one is 09. Okay. So what is which block the data will be stored? Block number 2. Block number 2. So block number 2. What is the tag? Tag is 00, and which data will be stored in block number 2? Let me tell you how to find it. So here is the way. So how you can find which addresses will be stored. So say 0, oh, say 000 01001. It's the same address of 9. So what should you do? Just keep this part same and change just the offset. So the offset will be 10. Again, keep this part same, 11, and again keep tag and block same, and 00. And what are these numbers? If you check these numbers, you see that these numbers are 8, 9, A and B. 8, 9, A and B. In block number 2, 8, 9, A, and B. Okay, now the next. So still for this one also we had a miss, because all these three access accesses weren't in the cache memory, and we had to grab them from the main memory and put in the cache memory. So let's go back to the next address. The next address is 05. 05. If I write 05 in the form of binary numbers, 05, it's here. So which block is that? Block number 1. Okay, block number 1, offset 1. Let's check block number 1, offset 1. Do we have it in the in our cache or no? It is in the cache. Okay, block number 1, offset 01. It has data of 5. Okay, so here we have a hit. We have a hit. So we don't need to copy anything from the main memory to the cache because 5 was there. It's correct that we haven't access to address 5 before. We haven't access to address 5 before. The addresses we accessed was 1, 4, and 9. But when we access to address 4, at the same time of copying address 4, we copied address 4, 5, 6, 7 because all of them are in the same block, and it's the reason that why address 5 is in the cache memory even without accessing it before. Okay, so any question?
No.
Okay, so now let me tell you. Now let's just continue. Let's continue. The next address is. I have a problem here. Is that my eraser is not working and I cannot erase all these lines. So, okay, so that's fine. So the next address is 14. Address 14. We want to access to address 14. So what should we do? We write number 14 in the form of hold on a second. Okay, I'm sorry. So address 14. Let's write number 14 in the form of binary. So it's 000 10100. So which block is that? Block number 101. 101. It's the block number 5. So we should put in block number 5. Which addresses? So which addresses? So let's do that. 000 101. So we say 00 000 10101 000 10110 10111. All of these 4 are in the same block. You see, all of them have the same block number 5. So these these bytes will be moved to block number 5. What are these addresses? These addresses are 14, 15, 16, 17. 14, 15, 16, 17 goes to block number 5. 14, 16, 17, 14, 15, 16, not 16. 14, 15, 16, 17 will be moved to block number 5. Do we have a miss or hit? Of course, we have miss because it was the first time. Very good. I have a question. You mean in the Kevin?
Yeah, wouldn't
ahead.
wouldn't 14, 15, 16 be and 17 be hexadecimal at this point?
Yeah, there are hexadecimal numbers.
Okay.
Yeah, we don't let me make it clear. In computer engineering we don't talk in decimal. So the all things we talk is hexadecimal and binary. Okay, so when I say 14, I mean 14 in hexadecimal. Okay, so forget about the decimal system. So anything we discuss here is in hexadecimal and binary. You got the answer?
Yes.
Okay, good. So we had a miss. Next address we want to access is, oh, finally, I think, okay. So the errors. The next address is, oh, it came back. The next one is 021. 021, not 021, sorry, 21. That zero was the like hexadecimal. 21. Let's write a 21 in the form of binary. If we write 21 in form of binary is here, and this 21 is hexadecimal. It's not decimal. If we write in the hexadecimal binary, so which block should we use to store this information? Who can tell me? Answers. So block number 0. I got, yeah, I got 1, 2, 3 answers. The block number 0, because the block field has number 0. But block number 0 is occupied before, and unfortunately I see that some of those blocks that we wrote before are erased. So okay, some of these blocks are just being used, and I promise that to reinstall my Windows and all applications again, because you see it's messy like. So block number 0 is already taken by some information. So we need to just erase those information and rewrite the new information. Okay, now I have a question that I want to make sure which addresses. You can see the answer on the on the slide, but do not look to the answer. Just please try to find it yourself. Which addresses will be transferred to the main memory when we access to address 21? Which addresses? Just repeat the same thing I did. So say
21. Wouldn't that be 21, 22, 23, 24?
21, 22, 23, 24.
Yeah.
Okay, any other answer? It's not exactly correct, Kevin. I got a few. Ryan gave me the correct answer. I see here. It's not. It doesn't start from 21, because this 21 is, like, doesn't have to like with the beginning of the block. Let me just show it to you. 21 is 001 00001. I said that like we can change the offset and keep the block and tag same. So you see the offset is 01. So we should consider the address before 01, which is 00,
Gotcha.
01, 1011. You got the point? So
Yeah, so it's 20, 21, 22, 23.
exactly. So
Yeah.
like it's moving the block. So any address we reference is not like to be the beginning of the block. It could be in the middle of the block, at the end of the block, but we transfer that specific block to the address. Okay. So so at this moment, the block number 0 in the cache memory will be the data, existing data will be erased, and the new data, which are 20, 21, 22, and 23, will be placed in that in block 0 of the main memory. And the last line is address 01. Address 01 has like this address. It was there just right a few minutes ago before we execute address 21. 01 was there. You see 01? 01, let me just use my
Yeah,
array.
it goes into block.
Yeah,
0.
block 0. It was there, but we just erased it and replaced it with 20, 21, 22, 23. And so what should we do? Again, we need to erase 20, 21, 22, 23, and again put 0, 1, 2, and 3. Okay, because we need that data. And here also we have miss, because it's correct that the data was there, but at this moment that we want to access to that data, it's not there. Okay, So it's the way that cache memory in direct mapping works. So next week, so we have like exam, and then I will talk about set associative and repeat the same example we did for direct map for your for the other mapping methods.